Hello students, welcome back. We just had a thorough discussion on the theory of confidence intervals. It was long and deep, but necessary. Alright, now let us solidify our understanding through a couple of example problems. And here's one. A certain college selected a simple random sample of 126 commute students and obtained the students' one-way commute distance. The resulting sample mean was about 10.22 miles. Estimate the mean one-way commute distance of all commuting students of the college using the standard deviation of 6.2 miles approximately. And then here are the questions to answer. What is 95% confidence interval? How about 98% confidence interval? And then a couple more about confidence bounds, which we have yet to discuss. Okay. Before starting A, let's analyze this problem a little bit further. The problem gave you three numbers. First, the sample size of 126, that's pretty straightforward. And then the sample mean of 10.22 miles. Finally, the standard deviation. Okay, these are the numbers the problem gave you, but you can immediately find out the standard error, which is sigma over square root of n, and thus this is 6.2 divided by 126. The square root of 126, excuse me, and that is approximately equal to, well, you can find out by punching in the calculator. Alright, 0.55 something. Okay, that's what this problem gave you. Now let's find the 95% confidence interval. This is a normal problem, so a picture is absolutely necessary. But I'd like to save some time. Instead of going to drawing mode and drawing a picture with my mouse, which is really lousy, I'll copy and paste the previous picture here, created for 95% confidence interval, and go from here. The center here is x bar, that's 10.22, and then 95% here blue, which means the other 5% must be shared by the left-hand side and also the right-hand side. And then we are looking for the interval, left-hand side endpoint here and the right-hand side endpoint there. So basically this is what we want. That is left-hand side endpoint and the right-hand side endpoint. And that's approximately equal to what? And that's the structure of the problem. Make sense? What you want is the left-hand side endpoint and the right-hand side endpoint. This value here and that value there, or equivalently speaking, the center, the best point estimate, minus a certain margin of error, which will give you the left-hand side endpoint, and then from the center, plus the margin of error, that will give you the right-hand side endpoint. Okay, that's a strategy. How do we do that? Well, here is solution number one. Of course, you need a picture. And then let's begin with the z-score formula. N minus center over SE. That goes with the picture, as a matter of fact. Now, this z-score formula has many, many versions. X minus mu over sigma, which you saw, and then x bar minus mu over sigma over square root of n, x minus x bar over s, mu minus x bar over s over sigma. There are too many, impossible to track them all. So what do? Draw a picture, which I very strongly recommend, and then from the picture, you get this, N minus center over SE. That is the formula number 1 of this course in terms of the level of importance. So this formula number 1 actually includes the picture. And you can say this is picture number 1 as well. All right, now let's work it out. How many endpoints are there? Left-hand side endpoint and also the right-hand side endpoint. Which one would you like to work with? Me, I usually go to the left-hand side endpoint for the normal picture, and the reason is because the standard normal table, which I'm going to show you in a moment, is all based upon the left-hand side shading. And that's why I prefer the left-hand side endpoint. Here in the left-hand side endpoint where my mouse is running around, the left-hand side shading is 0.25%. Excuse me, 0.025, so 2.5%. So 95% here, 2.5% here. So look up the z-score associated to 2.5% or 0.025. Well, that'll turn out to be negative 1.96. Well, let's check. Let's go to the normal table. Yeah, left-hand side shading. And then let's find out 2.5%. Where is it? It's right here where my mouse is running around. Let's go to a drawing mode. You see? 2.5% or 0.025. And that's in negative 1.9 row and 06 column. So up to first decimal digit, we get negative 1.9, and then second decimal digit is 6. You get negative 1.96. That's the z-score associated to this probability, 2.5%. Does it make sense? Okay, let's get out of this drawing mode. And there you go. That's how I got negative 1.96. All right, we have an equation to solve, and let's solve it. Flip this denominator to the other side. Flip this denominator to the other side by multiplying it over. So we get this. And then flip this subtraction to the other side by adding it up. That's how you get this expression. 10.22 minus 1.96 times the standard error of 6.2 over square root of 126. Calculate that. I'm going to get the left-hand side endpoint, 9.14 approximately speaking. And also, look at the structure. Center minus the margin of error. So this got to be the margin of error, the radius, from here to there. All right, I got the left-hand side endpoint. I need to find out the right-hand side endpoint. How do you do that? You can go back here and then redo everything, reading the table and on, but that's an overkilling. We don't have to do that. From this picture, you can use the symmetry. From the center minus the margin of error is the left-hand side endpoint. Now from the center plus the margin of error will give me the right-hand side endpoint like this. This minus becomes plus. So if you find one, finding the other is easy. Now that we have L and R, put those two together as an interval, and there goes the solution. The 95% confidence interval is, approximately speaking, 9.14, 11.30, approximately speaking, of course. I did not specify how many decimal digits to take, so I'll accept anything. That's one way to handle it, and that is my method, based heavily upon the formula number 1, z equals to n minus center over se. Very good method, and you don't have to memorize a whole lot. Only that formula number 1 and the picture. But then again, there's some algebra that you have to do. Solving for L from here, and some students get bogged down here. And theoretically, if you're TSI compliance, then you shouldn't be having trouble here. But for many students, it's been a while since they took previous math course, so they sometimes struggle. So let me give you an alternative method. And the alternative method goes a little bit deeper at first because I'm going to do this symbolically, but it'll give you a formula in the end. So here it is, the normal picture, centered at x bar, which is 10.22, and minus margin of error plus margin of error. All right, and then you see z-score is end minus center over SC, and then there are two endpoints, left-hand side and right-hand side. So left-hand side, right-hand side, we have these two equations. Center is x bar. SE is, in this case, sigma over square root of n, but any SE. Now, in the left-hand side, I'm going to get a negative value for my z-score. And that's always the case. Here's a z-table, by the way. Whenever I have the left-hand side shading less than half, I'm going to get all the negative here. And then whenever I have left-hand side shading more than half, I have all the positives. That's because the center is 0 for the standard normal. So for for left-hand side, we have negative z. For right-hand side, we have positive z. And what is that z-score? You have to look up and find out that z-star value. It turns out that z-star is 1.96 for 96%, 95% confidence interval. But for different confidence interval, you have to read the table and figure it out. Now from here, solve for L and R, and that's simple. Flip this denominator to the other side by multiplying, and then flip this subtraction to the other side by adding up, and in the end we get these two formulae. L is x bar minus z star times SC, R is x bar plus of that, and this one is a margin of error. So you can write your solution like this. L comma R, the confidence interval, is x bar minus z score times SC, x bar plus z score times SC. Or you can use the idea of margin of error. Margin of error is z score times SC. So putting those numbers in, you get this computation. So the formula here, and then put all those into the formula. All those derivation here, all those symbolic derivation, even if you forget everything, as long as you remember the first line, you can do this. Not much of a mathematics, but it works. Of course, I am going to require to draw the picture. Otherwise, I'm not going to accept your solution. I'm going to require to draw a normal picture every single time normal shows up. So 40% is that picture. Otherwise, you can do it like this to the formula. Fair warning though, you don't really have to do solving equation or any kind of those college level mathematics, but putting those numbers in may look easy, but it can be deceiving because it deprives you a chance to think. So if you slip and then get something ridiculous, there's no way changing it, so you end up with losing a lot. And also, if you rely upon formulas too much, then pretty soon you'll have a lot of formulas to work with, and it's going to be very difficult to match which is which, who's who, what's for what. If you understand where everything is coming from, that formula number 1, z is n minus n2 over sc, and then take just a couple of algebraic steps, then you don't have a lot to remember. Just one formula and then you can handle it all. But if you remember, if you do not remember that, and if you rely upon formula method, then pretty soon you're going to end up using 24 formulas, which could have been written in only one expression. So that's a trade-off. In any case, choose your best method. Oh wait, one more thing. Yes, we have the second problem, 98% confidence interval problem, which of course comes with a little bit fatter picture, but you can do pretty much the same way. This problem is left to the students. Part B, I mean.